Sorry, you're muted. We cannot hear you.
Sorry. So today we'll be talking about logistic regression. For the multiple form of logistic regression is a multivariable method for modeling the relationship between multiple independent variable and a categorical dependent variable. So logistic regression analysis studies the association between a categorical dependent variable and a set of independent or explanatory variables. As I told you before, for linear regression, the outcome is continuous. For logistic regression, the outcome is categorical. Can you see? So for multiple regression, like any of them, you can have, of course, the outcome is usually one variable. But you can have one variable at exposure. That is simple regression, either linear or logistic. Once the exposure is only one variable, it's simple regression. When the exposure variable are more than 1, 2, 3, 4, and so on, that is multiple regression. So you can have multiple linear regression or multiple logistic regression. So the multiple regression, whether linear or logistic, is what we call multivariable analysis. So logistic regression is a type of generalized linear model for response variable where regular multiple regression does not work very well. When I say generalized linear model, so when we talk about general linear model, that is this one, when I say general, it means that it follow a linear model naturally, like linear regression, ANOVA. I've already said yesterday, ANOVA and regression is the same. ANOVA and linear regression, not just ANOVA and linear regression is the same thing. So the other one called general linear model. But when we say generalized linear model, they are part of the generalized linear model, but it now contains some other that are not linear naturally, but the way to solve it, you have to bring that linearity into it. We'll explain it further. So under the logistic regression, now you can have binary or binomial logistic regression. That is when the categorical variable has two categories alone, like alive, well, yes, no. No, when they have the exposure outcome variable has two possible values. That is binary. So when you have more than two categories of that, just know that the outcome variable is only one variable, but the possible outcome may be two, that's binary. It may be more than 2, 3, 4, 5, that's multinomial. If it is 3 and above and it's ordered, it's ordinal. So if it is matched, we call it conditional. But all those ones, what we are focusing on is a binary, because that is the simplest model for you to conceptualize is binary logistic regression. The name logistic regression is often used for the binary, yes. So sometimes when you say logistic regression, you just mean that binary logistic regression. The dependent variable has only two values. That's why it's binary. One of the assumptions of the linear model is that the relationship between predictor and outcome is linear, like that of linear regression. So we explain linear regression later. When the meaning of linear is that if there's increase in this exposure value, there will be corresponding increase in outcome variable. If there's more increase in social variable, more corresponding increase in linear variable. It may be an increase or decrease, but it depends on which type of relationship among them. That is linear. When the outcome variable is categorical, this assumption is violated. You cannot assume that it's linear. So one way around this problem is to transform the data using logarithmic transformation, which is a way of expressing a non-linear relationship in a linear way. So you got to see now, for you to use that regression model for a categorical outcome, there will be some transformation. And here is logarithm. Though there are other, they can use log, they can use probit, they can use log, but here for logistic regression is logarithm. Logistic regression use this transformation to express the linear model equation in logarithm term called logit. Logit. Logistic regression, logit. Now, the logic function is particularly popular because its results are relatively easy to interpret than all these probit complementary log function. However, it requires a logic link function. We're going to see. So, for you to understand it, look at the way linear, compare logistic and linear. Look at linear regression. You see what we did yesterday. There are many scatter point around. You can just draw a line of regression. But the logistic regression, because the value are concentrated on either yes or no. Some of them are one of them are zero. Some of them yes, some of them are no. There are two possible outcomes. You can see the way. So to just link them, it's just to link them with that. If you look at they are separate, they are not scattered like the other one. They are separate. They are grouped into two. It's either there or it's not there. So for linear model, you see the relationship is linear, while this one is called sigma S curve. Now, in this sigma, what it means that at the beginning, the relationship is slow. At the time, it just steep up, then slow. So it's very simple. If you look at the value are considered on two sides, either there or no. So when those ones that are no or yes, so if you look at it, they are together, but they are quite different. The no are quite different from the yes. That's why that graph is steepy. It's not like almost steepy as it is vertical. Now, how do you because when we talk about logistic regression, what they actually use there is odd. Odd. That is why when you are interpreting it, they say it's odd ratio they use as the statistic. And the reason they use odd and they use odd ratio is what we want to look at. Let's understand the concept of one, though we have talked about it before. When I was talking about measure of association, we were talking about odd ratio and relative risk. I gave you some clue about the difference between risk and odd. Odd of an event is the ratio of the probability that an event will occur to the probability that it will not occur. That is, P is the probability over 1 minus P. P is the probability that it will occur. 1 minus P is that it will not occur. So P over 1 minus P, that is probability that it will occur over probability that it does not occur. That is odds. Now, this thing I've shown you before, the relationship between risk and odds. You see, odds, as I said now, risk over 1 minus risk. Risk is the same thing as probability. Probability over 1 minus probability or risk over 1 minus risk. Why risk is odd over 1 plus odd. So you see, I show you if you calculate probability, calculate the corresponding odds. You will see that probability ranges from 0 to 1, odd ranges from 0 to infinity. And I also demonstrated for you, demonstrated during when we talk about relative risk and odd ratio, that relative risk also, it has limited range of value, while odd ratio is from 0 to infinity still. So if you look at it, if the odd or probability, if the probability cannot be less than 1, 0, cannot be greater than 1. So it's between 0 and 1. So it's just limited between 0 and 1, while the other one is from 0 to infinity. How does it relate? If you look at when the probability travels from 1 to halfway, is 0.5. The odd travel from 0.5 to 1. So when the probability travel the second halfway, 0.5 to 1, the probability travel from 1 to infinity. In the odd, rather, the odd travel from 1 to infinity. So it's a relationship between odd and probability. If you plot odd at the vertical probability, which is at the horizontal, look at it. You will see that the graph will never touch that one. If you look at the scale of the probability from 0 to 1, why odd is from 0 to infinity? That's why you just put 50 there, can be more up to infinity. So if you look at the relationship between them now, the thing will never touch 1 because the odd is going to infinity. So there are some other things here, So look at some of these logic behind transformation to logarithm. I think I explained that time when we were talking about assumption and hypothesis. You see number 1 to 20, I transform into logarithm. Look at the corresponding logarithm. If you look at it now, these value their whole number, but when you transform the logarithm, some of them begin to have decimal. So it gives you a impression that something that does not follow normal distribution, when you transform it to logarithm, it may follow. That's the logic between transformation we did at that time. So we introduce decimal there as if continuous. So you need to see that it shrinks for the smaller value, it expanded; for the bigger value, it shrunk it. So we may refer to the likelihood of observing an attribute as a proportion or as odd. If you want to guess, what is the likelihood of an event happening, you can use odd. And I told you those with the bets for football, they use odd because if you look at it, odd have a wider range from 0 to infinity, while the other one is small. One is 0 to 1. So it's 0.21, 0.211. As probability, they are not too, they are close, they look close. But if you transform them to odd, we're going to see more distance. So the corresponding odd of 0.21 is far, far higher than the is far lower than the 0.211. Can you see? So you give a gap so you'll be able to appreciate the difference very well. That's why those people that bet football, they use odd. So proportion are known to have a binomial distribution, which in turn converges to normal distribution when sample size increases. We know that anything that follows binomial distribution, when the sample size increases, it can follow normal distribution. That's what that law of the central limit theorem says. But the distribution of the corresponding odd is highly skewed to the left and will never convert to the normal. For the odd, corresponding odd, it will not convert to the normal. However, using logarithm of the odd instead of a odd result in probability distribution that converge to the normal distribution exactly as happened with the proportion. So if number one, you say the proportion, it doesn't you transform it so that there will be this element of linearity, but it will be skewed. But if you now odd is skewed. But if you now do the logarithm, it will make it look normal. The logarithm of odd, so if you look at it, it's not the logarithm of that, the logarithm of the odd. So logarithm of the odd is called the logit. Logarithm of odd, that is logarithm of p over 1 minus p is called logit. And we can work with logit in the same way we do with proportion. For example, because the logit are in a linear state, we can subtract two logit to find the difference between them. We could not do this operation with odd because they are not in linear scale. Logits are important also because the difference between the logarithm of two quantities is equal to the logarithm of the ratio of the quantity. For example, logarithm of A, log A minus log B, is the same thing as log A over B. Log C, look at it, log 6 minus log 2. The same thing as log 6 over 2. That is, if you calculate log 6, you calculate log 2, you minus it. It's like when you say log 3. So look at it. Now, look at it. Therefore, the difference between the logit is equal to the logarithm of the whole ratio. So this one just to give you some, look at this form is proportion. If the sample size increases the polynomial division, this is log, is cube. But when you now, this is odd rather, odds is cube. But when you now calculate the logarithm of that log, or it go back to normal. So with the logic, if you now want to, how do you conceptualize logic model? Just go back to what we did yesterday about linear regression. Since logistic regression calculates the probability of an event occurring over the probability of an event not occurring, the impact of the independent variable is usually explained in terms of odds. Because you are dealing with categorical outcome. So what you are looking at is that probability that it is male, male and female, you can give it. So odd of it is male, if the probability that is male over probability that is not male. That is the odd. So with the logistic regression, the mean of the response variable P in terms of explanatory variable L is modeled relating P and L through the equation. Look at, if we remember linear equation, we say y is equal to a plus bx. It's the same thing. Here is P, instead of calling y. Because what you are actually is the proportion that have the attribute is equal to a, which is alpha, this constant plus bs. The same regression equation, but in a different way. Unfortunately, this is not a good model because extreme value of x will give value of x plus b that does not fall between 0 and 1. It just start to tell you why we have to change to odd. So logistic regression solution to this problem is to transform the odd using the natural logarithm. With the logistic regression, we model natural log odd as a linear function of explanatory variable. Look at logit. That logit, y mean natural logarithm of odd, which is the same thing as natural logarithm p over 1 minus p. So that is the one that is representing y in the more linear equation plus a plus bx, where p is probability of interested outcome and s is the explanatory variable. The parameter of logistic regression are alpha and beta. This is a simple logistic model, just like the other one, like linear model. So taking the anti-logarithm of equation on both sides, one can derive an equation for the prediction of the probability of occurrence of interest outcome. Look at it. We will do the anti-logarithm, it will give you this. So eventually, all you just need to do, extending the logic of the simple logistic regression to multiple one may construct. Can you see? So that one I will just demonstrate is just for simple, that is one exposure variable. When we have more, 2, 3, 4, not like what we did for linear regression yesterday. So as you do, you get to conceptualize better. So odd ratio is a comparative measure of two odd relating relative to the different events. For example, two events A and B. The corresponding odd of A occurring relative to B occurring is the odd ratio. Odd of A over odd of B, that's the odd ratio. When a logistic regression is calculated, the regression coefficient beta is the estimated increase in log odd of the outcome value independent variable. It's not as straightforward as the beta for linear regression. In other words, the exponential function of the regression coefficient is the odd associated with 1 unit increase in independent variable. So logistic regression is one way to generate the odd ratio beyond two binary variable. So don't even do by yourself anyway. Just know that is the beta you get a calculate the anti-log. Is the anti-logarithm of that beta, which is regression coefficient, that give the odd ratio. And the odd ratio is very simple to is how many times the people that are exposed are more likely to have an attribute more than the people that are not exposed. When you see the example, we will understand better. Suppose we have a binary response variable and a binary predictor variable. And in addition, we have other predictor variables that may or may not be binary. So the curve, don't let me logistic curve, leave them one. Look at when I showed you the other time. Probability over Z log. So there are some of those things, the fitting of, I don't not bother you with all those fittings. Just like, it's easier to explain and to a linear model. But this model, you don't need to. No, we evaluate it also. After, remember when we plotted the graph for linear, we try to evaluate how good the model is by calculating the R square and the F ratio. Here also, there are different other way. Some of them are similar. We want to look, we want to see overall model relationship, the importance of each dependent, predictive accuracy, model validation. So we have likelihood ratio, omnibus test, pseudo R, or my lemma short show. That R square, that same R square is not so useful. It's there. But in interpreting logistic regression, the most important thing is for you to understand the odd ratio. All these other one, they are these words. Because I will tell you something about this word statistic when we run one, because it's a form of chi-square. So what I want to leave this about, let's just go to example. This is an example. Example of obesity and cardiovascular disease, CVD. Exposure is obesity, either obese or not. Yes, no. Outcome is this is just a simple one, simple logistic model, where of course the outcome is dichotomous. That is cardiovascular disease, yes, no. The exposure is also incidentally dichotomous. Obesity, yes or no. This is a simple one. So looking at the table now, there are 1,000 people, 300 obese, 700 not obese. 106 have cardiovascular disease, 894 not have cardiovascular disease. You can see 46 people, they obese, they have cardiovascular disease. 54 people obese, they do not have cardiovascular disease. 60 people not obese have cardiovascular disease. 640 not obese, do not have cardiovascular disease. So if you look at, I just want you to at least to understand something before you go around it. At least pick something. If we look at that equation, we say log G to Y, which is natural logarithm of odd, which is natural logarithm of P over 1 minus P. Now, for y, there are three scenarios here. Y without x. Y, x is there, but it's no. Y, x is y, is yes. What we see in the meanwhile, if we are not even considering obesity, people do have cardiovascular disease. There are some other things that, even without issue of obesity, you can say some people have cardiovascular disease, no cardiovascular disease. That's for Y without X. So Y with X, but X is no mean that, yes, you consider obesity, but obesity is no. Then X with obesity, yes, that you consider obesity, yes. Can you see the series scenario now? No, I told you before, when you are this this regression model, A is the constant, Bs. That A is the value of Y when X is equal to 0. That is the value of its outcome variable when the exposure variable is not even there. The particular exposure variable is not there. So let's look at the first one. For Y without X at all, so without considering either somebody to obey or not obey, you can see how many people, 1,000, how many have cardiovascular disease, 106. So the proportion of people that have cardiovascular disease is 106 over 1,000. But if you calculate the proportion of people that don't have will be 1984 over 100. When you solve it very well, it turn to 106 over 894. So the odds of being obese among the prediction of cardiovascular disease, rather, having cardiovascular disease, if you don't even consider obesity is this. So if you calculate the logarithm of that 106 over 894, it gives you minus 2.13227. B is equal to 0. So if you look at the equation now, we say BO plus BY is equal. So here now, that beta is the obesity. That's the only factor there, B1. So if the value of the obesity is not even there at all, so that shows that B1 times 0 is out. So that B0, which is the constant, that is the value, minus 2.1327. When the obesity is considered, there is no. So what happens? You see, among the people that are not obese, what is the odds of having cardiovascular disease? Is 60 over 640. Look at the no. So when you now calculate the logarithm, they give you minus 2.367. So you remember, yes, the obesity is considered by is 0. So it will still give you, can you see? But the third scenario, for when obesity is weird, that is, so the odds of cardiovascular disease is 46 over 254. So when you now calculate the logarithm, it gives you the, and you mind you, the value of obesity is 1, that is yes. Logistic, you coded it 1, yes, no, 0. So yes. So that shows that if you bring the equation out, it's going to be minus 1.70869 is equal to BO plus BY. And so if you now remember, what did we calculate for B, this second one? The value of B0. If you substitute it, you put it there, you'll be able to have your B1. So we have B1, we have the B0 also. We also have the B0 when obesity is not considered. So odd ratio now will be the exponential, that beta. Those beta, beta 1 over beta 0. Beta, this second equation, that is when obesity is yes, is beta 0 plus beta 1 over anti-logarithm of beta is 0 when obesity is known. Can you see? So at the end of the day, when you calculate the anti-log, it gives you the odd ratio. So the odd ratio is 1.9. If you calculate the odd ratio with that now, you get the same thing. You remember the way we calculate the odd ratio with hand. Just say 46 times 60 is 40 divided by 25 divided by 254 divided by 60. How am I calling? You can try it. If it's just to cross check what I'm saying. 46 times 640 divided by 254 divided by 60. Yes. It gives you 1.9317. That's the odd ratio. So let's run I didn't share that with you. I forgot to share that data. The data is here, we are going to use it also. That one is for Titanic. Let me share this data. This one was just solved now. I will do it. Then when someone will now share the Titanic, if anybody, it's only two of us, you. Oh God. Now wow. Okay, I think did I even okay, let me go to just a minute. Obesity and cardiovascular disease. So let me share. Can you see my this thing? So look at this data set. This one I just did now. If you want to confirm it, that is data set. The total is 1,000. If you scroll down now, it's up to 1,000. Up to 1,000. Look at it. It's up to 1,000. It's the data set. So we have the way we enter it, logistic. When I enter, if you want to do and calculate odd ratio by cross tabulation, you have to enter it 1, 2. That is, yes is 1, no is 2. But if you want to run a logistic regression, yes is 1, no is 0. Can you see now? So you have to prepare it. So that's why I see obesity logistic, CVD logistic. So that's what I want to do now. Let me just run the analysis. Analyze, go to regression, binary logistic. Yesterday we put linear. This one is binary logistic. So dependent variable is CVD logistic. Outcome exposure variable obesity based logistic. So you come click option. You now click CI for exponential B. I've already told you the odd ratio is exponential of beta. CI means confidence interval. If you don't click on this, look at it by default, it sets it at 95% confidence interval. If you don't click on it, it will calculate the odd ratio, it will not give you the confidence interval. So we now say continue. Okay. Let me share the output with you. You see, look at the output. You first of all see plus 0. Look at that first one. The first block is first of all tell you, okay, if you don't even consider obesity at all, constant included in the model, can you look at the beta we got? And 2.132. So when you now come another step, you include, look at the model, though it's not so useful. The R square 0.1. That R negative R square. Can you see? 1.2, but it's not useful. So the most useful of this table is the last one. You see the beta for beta logistic. You see the constant, that constant minus 2.367. When we say okay, obesity is there, but if it's no, look at what we got. Look at the worst statistic. Just a minute, one of the participants calling me. So now you see beta, you see standard error. Then this standard error is measure of how accurate is whatever you are measuring, the beta. Then we now have worst statistic. This worst statistic is chi-square. If you divide this beta, is it beta over standard error over beta? I think standard error over that beta, or is it beta over standard error? And now square, if you divide beta over the standard error, it follows normal distribution. But if you now square it, it gives you the worst statistic. It follows chi-square. In some software like Starter and EpiInfo, it doesn't bring this worst statistic. It brings Z. It's just the division of beta. I think it's beta over standard error. That beta divided by standard error, that's what they use. Because it's Z, it follows normal distribution. But when you square it, you remember the origin of chi-square to square normal distribution. If you square it, it gives you chi-square, worst statistic. And do this exponential. If you calculate the antilog of 0.658, which is the beta, it gives you that exponential b, which is the odds ratio. If you remember, that is the odds ratio we calculated, 1.932. And it also gives you 95% confidence interval. I don't think you have issue interpreting 95 because we have already, when we're doing odds ratio and relative risk, if it does not cross 1, it means that it's significant. This one does not cross 1. It starts with 1.28 1 to 2.91. So the range does not cross 1. It's statistically significant. Any question? Any question?
No,
Yes,
no.
we can also run, because in that data set there's age there. We can also, age now is quantitative within category. Did I categorize that age? Let me check. Because if you don't categorize, if you can run the age directly. We have already said that when you are dealing with logistic regression, it's the outcome that is categorical. The exposure can be categorical. It can be numerical. Let me see. We have age group here. We have age group. We have age directly. Can you see any of them? Because, it's age group. It's not age directly. 50 plus logistic. Okay. It's age group. Those ones that are more than 50 and above logistic. So let me include it in, just like the way we did. This one we just did now is simple regression, because only one outcome, which is cardiovascular disease, and one exposure, which is obesity. But if you want to introduce another one, which is age above 50 or not, I've categorized it also. I've created the dummy. So what I did is what we call dummy. If you let me, I think is this thing I'm sharing now. What I just shared is the data editor window. If you come to view here and remove value label, you see all those one. I just say CBD. One is yes, obese. Two, no obese. But for the one I put logistic, one is obese, is zero, not obese. So when we say age above 50, no means not above 50. Yes mean one above 50. So now let's run it. Let's now do multiple regression now. That is including both the obesity and age. So if you go there, regression, binary logistic. So you just move age 50 plus. Let me see. Please, who is mute? Mercy, I sent that thing to you now. We didn't see it. I even sent to the other number. That's why I forwarded when you were saying. So you see, come and see. You will see now, obese logistic, look at his own, look at age, look at the, when you are doing multiple regression, you remove confounder. You remember when we were talking about error in potential error measurement, we talked about bias, which is systematic bias, and one of them is confounder. So how do you remove confounder? We say that one way of removing confounder is statistical modeling by carrying out multiple logistic regression. If you remember, when you did only obesity, the odds ratio was 1.93. But when you now add age now, somehow, age and obesity, they are related. Most of the time, when people become age, if they eat, they continue eating, they will not burn, they become obese. Immediately become obese. So somehow, age and obesity can be related in this data set. So that is why when you now run it, imagine if it was not significant now, or if it was significant, later it's no more significant. Okay, look at the obesity now. If you look at it, it's no more significant. Can you see? Look at the whole, two ways you can know. Look at the p-value, 0.065. Or look at the confidence interval, 0.97 to 2.35. For you to move from 0.9, you have to reach 1. 1 is in between. You have to reach 1 before you can reach 2 points. So that range of value 0.974 to 2.355 at included 1 is no more significant. The age is significant here. So those ones that have age 50 and above are more likely to to be obese is 1.96. So you can see now, maybe age was confounding for that obesity as a factor for cardiovascular disease. Can you see? So when we run it together now, age is significant, the obesity is no more significant. So I want somebody who has the data for Titanic so that we use it to do question. Who has Mercy? You have it now. Dr. Dimas.
Yes, sir.
Who will share Titanic? There's a data
Doctor,
set.
good evening. I did not connect with my laptop today.
Okay.
Yes,
Rachel,
sir.
you don't.
Let me share.
Okay.
Sir, you have to allow me to share.
Okay, sorry. Sorry. You can go on now. Okay. Yes. So this, let's go through. We have P class. Let's see first domain, second domain. Let's see what is there. Through this the data. Let's see the name of those variables. This data set you see the survivor of survivor per se is data set from those who were in that Titanic ship that sank in that early 19th. So you see what did make the people that survive different from people that don't survive, didn't survive. So survive is our outcome. Survive 1, did not survive 0. Still scroll, you see the sex, you have still scroll. Scroll to the right. Let's see, after sex, there's age. All this dummy 1, dummy 2, I don't know what. Dr. Dima here, so age, sex, there's some other thing. I know there are some. May wait, may sex, may dummy, female dummy. Okay. First class dummy, second class traveling with. So there are some. So they wanted to know what made those who survive different from people that survive. It's like female survive more than male. Then whether you are traveling alone or you are traveling with somebody, the people that travel with somebody survive alone. They survive more. Whether you are traveling with family or not, people that travel with family survive more. Then the people that take first class survive more. So let's go to analyze. Let's see. Though in doing logistic regression or regression, you will run your initial analysis. All this one I'm telling you now, how did I know that male, female survive more than female? I will have cross-tabulated male and female. Just ordinary chi-square cross-tabulation to know which one is common before you know all those things. And that is what even inform you to create the dummy. All these dummy now, I've created them based on those findings. Okay, logistic regression. Yeah. You move, survive is the dependent variable. Move it to that dependent space. No, up. That's covariate. Move it to depend. Survive is your outcome variable, is dependent variable. You see dependent up now. Return it and move it up. That arrow up. That arrow up now in front of serial number, that arrow. So for covariate now, you can put age as a raw value there. Put age there as the way it is raw value. Age as covariate. Scroll down to pick this other one. Female sex. The one I call female sex, what I just here, the one I coded female one, male. When we say male sex, male one, female sex. So click on female sex. Female sex, look at it now. Female dummy, rather, don't worry. Female dummy. Traveling alone. Movie there, traveling alone. Oh, don't worry, no. Remove travel alone, put travel with family. Travel with family. Because that's the opposite of that travel alone. Traveling with family. First class. Click on first class. Okay, let's run this. Let's see. Before you say okay, option, click on option so that you put click CI for exponential confidence interval. CI for S. Click on it. If you don't do it, I will not give you 95% confidence interval. So continue and okay. Stop sharing and share. Stop sharing and share the output for us. Share the results. Inclusion. Yeah. Expand it. Let's see it very well. Okay, scroll. Okay. Scroll to the last one. Let's see. Go to the line. Thank you. You will see, go straight to, if you look at the age, is significant. But if you look at it, what is telling you as the age increases, you are less likely to survive because they consider female, they try to consider female and young people when they were giving them this life jacket. They don't have enough life jacket, no enough boat, safety boat. So if you look at it now, the odd ratio, though is significant, but it's less than 1. It means that as the age increases, the likelihood of surviving decreases. So that means that as the age decreases, the likelihood of surviving increases. Then you look at female. Female survive more than male. Female are 12 times, 11.8 more likely to survive than male. Then traveling with family, 1.1 times, that is, you are slightly, it increased by 11%. Your chance of survival increased by 11% if you travel with your family. Have traveled alone. Then first class, can you see? The people in first class are 6 times more likely to travel and to survive than people in. Imagine now, if I put traveling alone there now, it will give me the same because it's travel it's either if travel with family or travel alone. It will give all those bitter and not bitter, all those standard error and worst statistic will be exactly the same, but the odd ratio will be the one in opposite direction. It will be less than 1. Because so sometimes when we have analyzed in the data, it may give us clue on how to do the determine. Because we don't want, we prefer, apart from the age now, just using naturally like that. If let's say we decide to decide the group age to old and lower and younger people, we can now make the older people reference. So our odd ratio will be greater than 1 because we are trying to look how many times the people that are younger are more likely to survive. They will just put in the age like that. As the age increases by 1 unit, the likelihood of survival, we know that it reduces, but it's significant. If you look at it, I say that it will either, whether it's less than 1 or greater than 1, if it's going to be significant, it will not start its 0% and end in 1. Look at it now, end after 1. Look at that first one. The odd ratio is 0.97. From lower limit 0.96, upper limit 0.98. So you can see it has not crossed 1. It means significant. Look at this one that is 11, odd ratio 11.85. The lower limit is 8.5, the other one is 60.4. The same thing with the traveling with family, 1.1 from 0.8. Okay, that one, if you look at it, is not significant. Even the p-value is not significant. Can you see now? It has started from 0.8 and end at 1.5. It has crossed 1. So, because if it's not significant with confidence interval, it will not be significant with p-value also. Look at the first class, 6.123. Lower limit is 4.1, upper 9.1. Any question? So, when you are showing your multiple regression, the thing you show is that you don't need, so when you can show beta, standard error, what statistic, this degree of freedom, you can remove it, put p-value, put exponential, which is this exponential b, you call it odds ratio. The 95% confidence are all lower and upper. You put it like that. Many people, they don't know that, okay, if some people cook, some of the when we're doing the MPH, some people say, go and do regression. They want to put some figure there. They don't know that there's a way we can check. Because we know that beta over standard error square, it gives you the worst statistics. And the L ratio is the anti-logarithm of beta. So if you put just any figure there, you put or just cook some figure. By the time we cross-check, we know if you are cooking. And the scene is not available. So, any question?
No question.
No, are you sure? Okay, there's no question. We do everything. So that's the end. There's no question. So you can lay your hand on all these lists that I go and be running in, on the data set and see how it is being done. Okay,
Please,
thank you.
if I may ask, what's the main difference between linear regression and logistic regression?
Main difference in what sense?
Maybe in the sense of the relationship between, the independent and dependent variables, like,
It's the same thing now. It's the same thing. The only thing is that for linear regression, you use when the outcome you are measuring, like blood sugar, something that is already continuous. Continuous variable is the outcome.
Yeah.
And the exposure can be continuous, it can be categorical. And in the categorical, you do dummy. We mean of dummy if something is two male and female. You make one man.
Hello?
make it 1. When the attribute is lower, for example, that we know that female survive more. We now say female 1, we coded female 1, male 0. So that when we run it, you give you odd ratio that is greater than 1. If there is a relationship, it will not. If you give odd ratio less than 1, it doesn't change anything, but it may influence your interpretation. So the dummy, you need to create, once you are not using quantitative variable, once it's categorical, whether you are doing linear or logistic, you must create a dummy, and that dummy is 0 or 1. So if you are talking about maybe educational structure that have about 4 levels, you can make the first one no formal as the reference, where you compare, you create the dummy for the other one. So what it means that for you make the whole of the reference 0. Then primary, anyone that is primary, put 1, everything 0. Secondary, anyone that is secondary, you put 1, another thing 0. The tertiary, anyone that is tertiary, you put 1, everything 0. That's way to create a dummy. You get it now. So that's the way to create it. So you create a dummy. So there's no difference. The only difference is the outcome for logistic is categorical. For linear is quantitative, or most of the time continuous. So, but the only thing, the interpretation, because we majorly used that R square is very, very important with linear regression. R square and F ratio, especially that R square. Whereas here is odd ratio. Elizabeth is odd ratio. In linear regression, that R square is very, very important. R square, then beta. You now look at R square, beta, and whether it's significant or not. But for logistic, it's odd ratio. In the confidence interval, that odd ratio that is very, very important. And you can know even with that p value, you can know if it's significant. Any other question?